So let's go ahead. The thing we're going to look at today is this phenomenon referred to as tunneling. This idea that we can get a non-zero potential inside of an energetic barrier. Now, in classical mechanics, if we set up a problem, we're going to look at a particle in a well. I prefer the particle in a well problem. Your textbook does the potential barrier. We'll look at the potential barrier as well. I just prefer particle in a well because I find that it relates to physical systems and chemistry a little bit better. So when we're looking at this particle in a well, we're essentially going to say I've got some zero potential, then I've got some dip, and I'm making it infinitely sharp, right? That's not something that would happen in nature. I've got some space there, and then it goes back up to zero. It does not go all the way to infinity, right? I've got some potential here. I've got some other potential here. We can say the bottom of the well is our potential 0, so that way it's the same as if we're in here, and we can even say that the bottom of the well goes from 0 to L. That means if we're inside this well, we're going to do the same thing that we did for particle in a box. We should see the same types of solutions. If we're outside the well, originally, and I'm going to label this as region 1, region 2, and region 3. And originally what we said was if you're outside the well, your wave function was 0. But that was because the potential went to infinity. What happens if our potential does not go to infinity? Kind of what like we see in the harmonic oscillator, and also we would see in this case. I'll start with region 2 because that's kind of the easier one to think about. We've already thought about it to some degree. If I'm looking at my wave function, well, first let's look at the Hamiltonian in region 2. The Schrödinger equation would be the same Schrödinger equation we had for particle in a box. We would have a p squared x hat over 2m on psi is equal to, let's see, I want to include this other term here just for a moment. Vx on psi is equal to E on psi. And for this is going to be, and I'm going to put a little Roman numeral 2 at the end of each of those psi's, because this is particularly looking at region 2. Right? And in this case, if we're in region 2, this term can just go to 0. Oh no, I haven't forgotten my negative yet, because when we square that, we get a negative sign. When we solve this, we're gonna go ahead and plug in our answer for our operator for px squared operator, our momentum in the x direction. Switch all of our constants around, and we're gonna get a d by dx squared psi in region 2 plus 2m e on h bar squared psi in region 2 is equal to 0. Same thing we did for the particle in a box. Exact same. Now, the catch is there's going to be 2 catches. But the first thing I want you to notice is because we are in this region where the potential is 0, we're in this situation where energy is greater than the potential energy. And when the energy is greater than the potential energy, that's where we get these oscillatory solutions. These things that look like sines and cosines, e to the I kx. When the energy, and this is the big thing to learn from tunneling, that's important to us. When the energy is greater than the potential, we get oscillatory answers. Did you ask why? Why? So if we just set this up, if we call this some a squared and we look at what things solve this, because the 2 things need to add up, it's going to be sines, cosines, e to the I kx's. Right? Now, let's consider something we haven't looked at before. Let's consider this first region or the second region and see how that's going to change things a little bit. So if we're looking at region 1, which should be the same as region 2, should be the same as region 3, we can see how it's going to be a little bit different in this case. In this case, I'm going to start out the same way. I'm going to skip this first one. I'm just going to set this to non-zero. I'm going to have d by dx squared psi 1 plus, oh wait, I've got to do this in more steps so I don't mess up my negative signs, because you know how I am with negative signs. I'm going to have negative h bar squared on 2m d by dx squared on psi 1 plus v. I'm going to call it v naught. I'm going to say if we're up here at this top part, that's some potential v naught plus v0. It's just some constant value. Psi 1 is equal to e psi 1. I'm going to have to multiply through and subtract the e over. So I'm going to get my d by dx squared on psi 1. I'm going to multiply by 2. I'm going to subtract. Here's what I'm going to do to try and make this a little bit easier. Negative 2m h bar squared. I'm just going to subtract this over, so I've got a v naught minus e psi 1 is equal to 0. Right? So I subtracted my e over before I multiplied just so I could keep that factor out front. But notice we get something funny out of this. We get this v naught minus e term. In the case where e is larger, this situation where e is larger, this term is going to be negative. This whole thing is going to be positive. It's going to look like what we did already. Do you all see that? Take a moment, think about it. Think about the case. If e is larger than v, and I'll even put the naught there. If e is larger than v naught. Oh wait, no, this is larger than v. So if e is larger than v, when our v is 0, e is larger than v. When our v has some value, I could imagine having my particle all the way up here above the barrier. And if I'm all the way up there above the barrier, I should have something that looks like a free particle, something just wiggling along like a wave, like we saw before. But what if I'm down here? What if I'm below v naught? Right? So we've got two conditions. If e is greater than v naught, then v naught minus e. I didn't give myself enough space. Then v naught minus e v naught minus e is some negative thing. I could bring that negative out. This whole term is going to be positive. I'm going to get the same thing. Here's the weird one. If e is less than v naught, then v naught minus e is positive. This is weird for two reasons. Reason number one, this is weird. In classical mechanics, if your energy is lower than your potential, you get nothing. Nothing happens. You can't have your energy lower than your potential energy and see something happen. You can't exist someplace. This region over here, if your energy were like here, if that's your E, this region over here, region 1, would be called classically forbidden. You would hit your potential and you'd bounce off of it. You wouldn't exist inside the potential. This, I know I've warned against classical analogies, but I'm going to give you a classical analogy to show you how absurd this is. This would be like if you were running and you ran into a wall, and instead of bouncing off the wall, you existed inside of the wall for a little bit and then bounced off the wall. Just doesn't happen. And then the wall's unscathed. The wall still just looks just like the wall. It's not like you dented it. You exist inside the wall and then you come back out. There's no real classical analogy. We can say this thing that sounds really silly because it is in the classical world, but in the quantum mechanical world, we get something that's a little bit different. If this thing is positive, I'm going to go ahead and do the same thing we did before with a slight change. I'm going to define my d by dx squared of psi. I'm going to call this whole thing some, we traditionally use the term kappa for this situation, so I'm going to call that whole thing kappa. Actually, I'm going to do you one better. I'm going to call it kappa squared because we're taking second derivatives. We could call it kappa, then we'd end up with a bunch of square roots. I'm going to go with kappa squared. Kappa squared psi 1. This change from the positive to the negative is going to make it so the solutions here are not sines, cosines, e to the ikx. It's just going to be stuff like e to the negative kappa x. Take the derivative, I get a kappa out, take another derivative, I get a negative kappa, take the second derivative, I get a second negative kappa. These two terms cancel. It's going to, and we did a problem like this when we did our first mathematics worksheet. We did this problem where we had the negative here. And this, instead of giving us an oscillating function, is going to give us an exponentially decaying function. So we're going to essentially see something funny happen. We will, and I'm going to sketch it, and then we're going to talk about how we would get this whole answer. I would have some wave function. Oh, that's not my pen. That doesn't work. Ah, there it is. We'd have some wave function in here that's going to look like our oscillatory system. And then on the outside, I'd have some exponentially decaying system. That's just going to decay out. The answers inside the well are going to look very similar to what we've done with particle in a box. Sorry, the answers inside the well. Inside, where I'm pointing, not what I'm thinking in my brain. The answers inside the well are going to look very similar to what we've done with particle in a box. The answers outside the well are going to have this weird exponential decay term. And of course, the first interesting thing that we all want to know, how far does it go? How far does this tunneling phenomena where we go into, the reason it's called tunneling is because it's like you're going into a mountainside. You know, you're just like inside the mountainside without actually digging. So how far will it go through that barrier? Notice that in this system, we've actually changed our boundaries. Not for inside the well, but we've got boundaries for inside the well. And then we've got boundaries outside the well, which would be out to positive infinity and out to negative infinity, right? So if we wanted to look outside in region 1, I'd be going from negative infinity all the way up to 0. If I'm looking in this region outside the well, I'd be going from L all the way up to positive infinity. Inside the well, I'm doing my 0 to L thing. Now, this is the part where it gets really complicated, and we don't actually typically solve this in an intro quantum class. Because what's going to happen is we're going to essentially have 3 different wave functions for our 3 different regions, but they're still going to be beholden to some important things. Psi 1 is going to have some a e to the minus kappa x plus b e to the positive kappa x. You can check, those are both solutions in that region. Psi 2 is going to have some c e to the minus ikx plus d e to the positive ikx, just like we've seen before. I've got it written as signs here. Remember, we switched to signs because it made the boundary conditions easier. It turns out when you're doing particle in a well and your boundary conditions are not as nice, it's actually easier to use the exponential terms. And then we'll also have region 3, which is going to be E capital. I'm going to change that because I don't want to use E because I already use that for energy so often. I'm going to call it F e to the minus kappa x plus G e to the minus, e to the positive kappa x. Yeah?
In region 2, it's just K, not kappa, right?
Yes, that's just K. So, and this is traditionally what we did with our other systems. We defined that thing as K squared. So in region 2, we're using K's. In region 1 and 3, we're using kappas. So this is the point where all textbooks kind of bail on you. And this is the point where I am also going to bail on you. Not entirely. I'll do some explanations as to why most textbooks and why we're not going to solve this in this class right now. In order to solve this, right, we still have to have the wave functions smooth, continuous, finite, all of those things, single valued. These functions are all single valued, so we're good there. But in order to make this smooth and continuous, I've got a boundary condition at 0 where psi1 and psi2 have to relate to each other. They have to be the same value and have the same slope at that boundary. And I've got the same thing here at L. I've got to have psi2 and psi3 equal in value with the same slope at that boundary, so I'm continuous and smooth. That means in order to solve for these 6 things, you essentially have to set up 6 equations with 6 unknowns. We're going to simplify a little bit. Since it needs to be single valued, as you go towards negative infinity, one of these terms, this term, as you go towards positive infinity, this would go to infinity. So that term you can just ignore already. This one, as you go towards negative infinity, this thing's going to crash out like it should. This thing would go off to infinity, so we can ignore that term. So now you've only got 4 things, but you're still going to have to do 4 equations with 4 unknowns. It's going to be your smoothness, so your differential, your slopes at the 2 boundaries, and your values at the 2 boundaries are going to give you 4 equations with 4 unknowns that you then have to solve. It's a huge headache. And typically, you get things where you can't explicitly solve for these coefficients. You actually look at ratios of these coefficients in order to talk about how far this tunneling occurs. It's a headache. It's solving this. It's doable. It's not impossible. It's done in some textbooks. It's done on. You can look at it online. But the thing that most people jump to is they jump from saying this is going to go on forever, and they change it to look at, rather than looking at a particle in a well, where you just know it's dying off to some degree, the more interesting thing to look at, if we're going to go through this trouble of solving for all of these different coefficients, the more interesting thing to look at is, what if this didn't go off forever, going all the way to positive infinity, but what if it just dropped off at some point where you've got some non-zero probability? This is tunneling. This is ending up outside. So you notice with this barrier here, I should still have an oscillating value in here. I should still have a decaying value here. But now I've got some possibility of having some oscillation out here as well, because I'm going to end up in another region where my energy is greater than the potential. So I'm going to reframe this problem a little bit so I don't have something as complicated up there. I'm still going to have a similar set of equations, but I'm going to set it up, instead of looking at the particle in a well. I find particle in a well much more useful than tunneling. The reason is because when you're looking at chemistry, essentially you can approximate any nuclei as an attractive force over a certain space. And so you can look at it as a potential well, as something that's got that attractive capability. And so it's a very rough approximation. Using the harmonic oscillator is a little bit better, so you've got that smooth transition rather than the sharp transition. But particle in a well can be used to look at these types of places where you get atoms, electrons, particles stuck. So it's a little more interesting. But tunneling, even though I say it's a little more interesting, I say it's a little more interesting because I'm a chemist. Tunneling, though, looking at it, rather than looking at all of that, we're just going to look at it in terms of one barrier, where you've got your region 1, your region 2, and your region 3. This is going to go from 0 to some width. This is going to be 0. This is going to be V0. It's almost like the problem we did before, except for now I'm just zooming in on this end possibility. It's going to have essentially the same setup. It's going to have the same ideas, except for I'm going to have oscillation, decay, oscillation, rather than decay, oscillation, decay. When we go through and solve this, there's the thing that is important out of this. The part that most of us are interested in. I got to give myself a little bit more space. I put the 1s, 2s, and 3s right where I want to write. So in this region, where my potential is 0, I'm going to have some oscillation. I'm going to have, it's going to, I want to change this oscillation a bit. I'm going to have some oscillation. I like that one better. I'm going to have some oscillation. And then when it's going to hit the barrier, I'm going to have that second thing happen where the potential barrier is greater than the energy of the particle. I'm going to see that decay term. And if it doesn't decay all the way to 0, I'm going to get some little oscillation out the side. And the question becomes, how much gets transmitted through? Yeah?
Are they supposed to both be zeros? Or...
Oh, so this is potential equals 0. This is x equals 0. Sorry. X equals W. Potential equals V0, potential equals 0. Thank you for that clarification. Yes, question over there and then up here.
You might get to this in a bit, so probably but how, if we can have like a continuous spectrum of barrier width, how do we go from one discrete wave function to a different discrete if we can change that width of such a decays?
Oh, so how do we get like something out here and something over here?
Yeah, like an n equals 1 on the right and from an n equals 2 on the left before it touches it.
So the oscillation would not change. It's actually just the amplitude that would change. I probably didn't communicate that well in my picture, but you would see that I erased the functions, but you would see that essentially you're going to end up with similar functions. You know, your energy differences are going to be changed. That's going to change your amplitude. But actually going through the barrier, you probably would see a change in the oscillations as well, because you are going through an energy transition as well, right? You're going to lose energy through this process. I'd have to think about that a little bit more to get it exactly right, but you're interacting with a new system. You're going to have a different problem to solve. Question? No? Okay. So what happens is, if we just want to talk about this change in amplitude, how likely it is for this to happen, we get a pretty lengthy equation. The textbook had a great quote. They set up the problem relatively quickly, and then the quote was, after a lengthy algebraic manipulation, and then they just give you this equation. And that's essentially what I said as well. That's what most textbooks say. We could talk about these solutions and the tunneling coefficient, the transmission coefficient. That is to say, the likelihood that you have some amplitude on this other side after you go across is going to be 1 plus e to the positive kappa w minus e to the negative kappa w divided by 16 e over v naught minus, oh, I feel like I have a typo. I hate it when that happens. 16 e over v naught squared, all all to the -1. So this all has to be underneath a fraction. I'll remind you that W is the width of this barrier. So we can play with a couple different ideas and see what happens. We can say, what happens if this barrier gets really, really narrow? Well, then we're more likely to see transmission happen, right? If we change this W to get to a large value, we can see how that changes the situation. What if the energy is much larger than the potential? If the energy is larger than the potential, we're going to get some weird solution down here. What happens as the potential gets really, really high, as V0 goes to infinity? We're going to essentially end up with a 0 on bottom here. We're going to get nothing getting through, right? We're going to get back to our particle in a box situation. So there's a couple different things we can look at. I want to remind you as well, I guess we've got the reminder up here, that kappa term has mass buried inside of it and a difference between V0 and E buried inside of it. So there's a couple different things that we can look at to say, how does this change? We can look at mass. We can look at the width. We can look at V0. We can look at E. And we can say what happens for each of these things. As we increase the mass, as the mass gets really, really large, we should see no tunneling occur, right? So as the mass gets really large, this tunneling coefficient, this transmission, should go to 0. Makes sense. Big things don't tunnel. As the potential barrier gets really, really wide, we're also going to see that tunneling go to 0. Makes sense. Since we've got an exponential decay in this classically forbidden region, the exponential decay, if it dies out before the barrier ends, you get no tunneling. It doesn't happen. So that's the other thing we can look at. We can look at the potential, the height of that barrier. The bigger the difference between E and V0, the faster the exponential decay occurs, the faster it dies off. So if that V0 is really, really tall, it's going to decay much faster. You're going to see less tunneling. The thing that's interesting, and then energy, as energy gets smaller and smaller, you're going to see less tunneling as well. Again, because it's really, when I look at these two, I really want to look at these two relative to each other. I want to see how that fraction E over V0 and that subtraction V0 minus E change and how they affect it. So there's a couple places where this happens. There's a lot of really interesting aspects in chemistry where the tunneling correction actually matters a lot. We also are going to see this happen in the harmonic oscillator. The harmonic oscillator can have amplitudes that are in the classically forbidden region. They exhibit some tunneling, kind of like over here, where you have some probability of being further along than you expect. You have some probability of being past the well. Same thing happens with the harmonic oscillator. You have some probability of essentially your pendulum swinging a little bit further than expected, and then going back to normal. There's some probability of finding it in these regions. Yeah?
Is there less energy there's less time?
With less E energy. So if and again, it's because if E is smaller, then that's the same as making V0 look larger. Oh, right, that's what I was going to say. So the places where we can see a lot of interesting phenomena with this, there's a lot of places where, in chemistry, where we see this type of situation. Everyone uses the example of walls when we look at this, but actually, if you looked at an example of self-protonation of water, right? This is an example. Now, the tunneling correction to this is like 0.1% or 0.01%. It's some small correction. But when you say, how much energy does it take for that hydrogen to actually hop over and make H3O plus and OH minus, self-protonation of water, autoionization. In order for that hydrogen to move across, essentially it needs to move through this space moving through that space acts like an energetic barrier. That acts like an energetic barrier. And so when we look at the probability of this proton being on this group or this proton being on this group, we can say that there's some, like, you all know what reaction coordinates look like. You can draw your energy curves. There's actually some possibility to tunnel through the top of that curve and for the reaction to occur at a lower activation energy than expected.
Is that for like radical reactions?
It's going to depend on these types of ideas. So radicals are going to have, like higher energy situations relative to the barriers of occurrence. So you can see that happen there. You can really see this happen everywhere. But in most cases, when you're looking at actual chemicals with like even a proton, you're looking at like less than a 0.1% correction. So it's a small correction. It's much more interesting when you look at electron transfers, which would be more like the creation of radicals. Since electrons have less mass than a proton, they're going to have greater tunneling probabilities. So there's places in chemistry where we actually can see this and say, oh, that's a correction we actually need to worry about. I'm not sure. I mean, we can do calculations on that. This is also, actually, now that I mention that, this is also, I don't want to talk about it until after our midterm on Thursday, but this is also going to lead to, like, these tunneling calculations, particularly doing tunneling with harmonic oscillators, going to be part of your first MATLAB activity that we're going to do. So we'll look at that. I'm thinking about time. Oh my goodness, that took me so much longer than expected. Oh wait, that's where that is. Just trying to think about things I want to do the time I have. So I want to mention one other thing. I'll talk about I've got one note about the harmonic oscillator tunneling. I'll save that till after the midterm for when we're talking about our MATLAB activity. But I want to add a third problem to our repertoire. And that third problem is going to be particle constrained to a ring. Rotational motion. Is everyone okay if I move on from tunneling? Your book does a really nice kind of walkthrough of how you can consider these different ideas. So if you haven't been reading the textbook, please, I think I've said this before, you should read the textbook. You really should. There's a really nice walkthrough of how you can think through these different ideas. Yeah?
What type of problems are expected to be able to do in tunneling?
Conceptual, kind of like, I don't expect you to be able to write this down again. I expect you to understand which things relate to the probability of tunneling and which things affect the probability of tunneling. And then we'll get more into like what happens with the harmonic oscillator and tunneling as well. Again, I'll mention tunneling has a huge number of patents. There's an incredible amount of work. Tunneling electron microscopes are really incredible. They get us atomic scale like images. There's a lot of technology that's really fascinating that uses tunneling as its backbone. So scanning tunneling microscopy, like there's a lot of interesting things you can do with this, which is why it's worth 30 minutes right now. It's really worth it to think about this. Talk amongst yourselves for a moment. I'm going to erase all of this and we're going to move on to the next thing.
So a lot of this in the exams, like the textbook, read into that.
What do you mean?
Well, you're just saying like the textbook is essential to read into tunneling and learn those relationships between
The textbook does a lot more of the relationship.
which it seemed like you were emphasizing for like to know how to work with or how to describe on a exam.
That's a circle, right? Pretty much. Okay. So, did anyone come up with questions while you were talking amongst each other? Okay. So, if we wanted to think about so we talked about translation and vibration. Those are two important energy types. conservation of momentum is a huge thing. Another thing that's really important is conservation of angular momentum, rotational objects. So we want to start thinking about things that are constrained to move in some path. So if I've got some object, at a distance r from this path where it's going to rotate. Pretend that this is actually a symmetric circle, and I drew a nice circle. But this particle is going to have some momentum associated with it, and it's essentially going to just spin around this ring. In this case, I would have to look at the px squared over 2m plus the py squared over 2m. Right? I'm doing a two-dimensional system. I'm looking at how it's moving. Its x components, its y components are changing as it goes. The momentum is just going to keep it swinging in a circle. We can talk about why this happens, right? What's going to be this tether? For us, it's mostly going to be the Coulomb force that's going to be holding a particle in, but it can still like move around. And it turns out that if we tried to do this in terms of the x motion and y motion, it's a little bit of a headache. Did you have a question?
Is there like something under the
So we can reformulate this problem into, oh, this one? Yeah, we can look at this as like a, I'm just going to leave it as a p vector for now. It's going to have like an x component, y component, z component.
It just looks like there's something written on the circle.
It's an arrow.
Oh, that's an arrow. Sorry, yeah, got your question.
Is the py also like an operator?
Yeah. Oh, yeah. Sorry. Oh. Thank you. So essentially, what we're doing in this situation is we're saying that x squared plus y squared is equal to some constant, which we're of course going to call r squared. Right? That's how we define a circle. This allows us to talk about how a particle would move with this constrained position. In the future, we'll allow r to change as well. We'll allow the distance from the point of rotation to change as well. But for now, we're just going to say we're going to be stuck to this ring. It becomes easier when we're thinking about this. Instead of thinking about how the x and y are changing, it becomes quite a bit easier to instead think about how this rotational angle, which I'm going to call phi, changes. And essentially, that's going to allow us to collapse this to some other operator that's going to be something like a negative h bar squared over 2m r squared d by d phi squared. Very familiar to what we've seen in particle in a box, except for now we're doing it in terms of the rotational phi, and we've got this extra constant r squared. I know you're all frantically wondering, but how? How do you do that? And I'm sure you all love converting to spherical coordinates. So I'm just going to mention a couple things. I am not going to demand that you convert things to spherical coordinates almost ever. There's a couple things that we do need to know about how this is going to work. So the few things that we need to know are what the definition of the coordinates are in x, y, and z. I'm going to give you the three-dimensional space. We're almost always going to be working in three-dimensional space. I could give you the polar instead of the spherical and then be like add more stuff later. This is going to be a little bit easier. So we've got our x, y, z. You can see what happens if you did x squared plus y squared in this situation where if this is the phi, then the theta would be tilting down from the z-axis into the xy plane. And so in this case, our theta would be pi over 2. We can also think about the volume elements. Which become important for, the volume elements become important for when we're doing our derivatives. You're going to have a dr, r d theta, and r sine theta d phi. That's going to be important for when we do our integrals, which also makes it important to mention theta is going to go from theta is going to go from 0 to pi, and phi is going to go from 0 to 2 pi. So again, when we're looking at our integrals, all of that's going to become important. And I've kind of fretted and scratched my head over the best way to introduce all of this stuff. And I kind of decided I'm going to give you the answers that we're getting to, and then we'll see why those answers come about. So if we're looking at the things, so I figured I'd start by telling you the important things. And then we'll see how we get to those important things. So the important things are, we have some LZ operator. This is going to be the Z component of the angular momentum operator. It's going to operate on some function. Traditionally, we call that function a function y. That's going to depend on theta and phi. And it's got some numbers here, and I'm worried that if I write these numbers, you'll already get some ideas, but I'm going to write them anyway. We use just like for the particle in a box, we had n. For the harmonic oscillator, we had v. We had some quantum numbers that came out of our boundary conditions. These things that we're using for our volume elements are also going to provide us boundary conditions, right? If this particle is spinning around this circle, it better end up being the same thing when it gets to every point around that circle. It better be the same around the whole circle. So that's going to be one of our boundary conditions. That boundary condition is going to give us a counting number that we call m sub l. And when we're doing the theta part and we're also including three-dimensional rotation, we're going to get another counting number, which we traditionally call L, from our boundary conditions. And we're gonna get into how we get those from our boundary conditions. But again, I'm starting with the answer. So in this, if I operate LZ, and we still have to define what LZ is, we're gonna get ML H bar, same y function back. Eigenvalue problem. These y's, these functions y's, are going to be eigenfunctions of the LZ operator. These function y's, LZ, we're going to set up LZ so it's a Hermitian operator, so these function y's will all be orthogonal to each other. All of the things that we normally do. We're also going to have another operator, the L squared operator, which is going to be Lx squared plus Ly squared plus Lz squared. It's also going to operate on YL, m sub L, theta, and phi. And it's going to give us L times L plus 1, H bar squared, H bar squared. That's the answer that we want to get to. This is the thing that we want to understand by solving this particle stuck to a ring. We're essentially just going to be doing this first one. And then when we move to a rigid rotor and actually rotating in three-dimensional space, we'll move to this one as well. But really, I just want to focus on this LZ part for now and just stick with the problem that we've already written down I can also, I'm going to hold off on writing what these functions look like. They've got a bunch of pi's, cosines, things like that. These functions are called spherical harmonics, and they are solutions to the three-dimensional rotator. Right now, we're going to restrict ourselves to this situation where instead of letting theta run from 0 to pi, we're just going to say theta is equal to 2 pi. Right? That's going to make it so theta is a constant. Theta is going to be stuck inside the, we're going to be stuck in the xy plane if theta is equal to pi.
So theta is the angle.
Yeah, theta is going to be the angle like off of the board, right? In the z direction. And we're going to say, okay, let's just look at the theta is equal to pi situation. That's going to simplify things to some degree. What's sine of pi over 2? We're not going to rotate all the way around. Theta is going to be equal to pi over 2. So let's look at what happens when we restrict ourselves to that and we just stick with this particle in a ring. What's sine of pi over 2? 1. So our x and y are just going to be like a cosine phi, sine phi. They're going to be like the normal things we define. Cosine of pi over 2? 0. No surprise if we're restricting ourselves to just the xy plane. The z, there's no z dimension in this. So by restricting ourselves to just the theta equals pi over 2 situation, we simplify what we're looking at. That's also why we can simplify this operator to just that. So then, got to flip back in my notes, we're going to define an extra thing as well. And again, you can see how if we did x squared plus y squared, you're going to have cosine phi squared plus sine phi squared. That's going to be equal to 1. And we're going to get r squared. Right? All of those things that we have kind of simply pop out in that theta equals pi over 2 situation. Still, the derivation of going from like a d by dx to a d phi, that's a little bit more. That's a little bit more. We'll do that in the future. If you haven't noticed, there's a PDF on the PolyLearn page. It's only 14 pages for converting d by dx to d by d theta, d by d phi, d by dr. It is an involved process. It's completely doable, but it just takes a lot of time that I don't want to use in class. So we're going to essentially trust that we can do this rearrangement. I'll rewrite those in a moment. But essentially, what we're going to do is we're going to recognize that this mr squared is going to be a useful thing to redefine. Capital I, moment of inertia, right? This is essentially going to give us some way to talk about how far is the mass away from this rotational bit. You can notice that if r is constant, this thing is just a constant that's related to the mass and the distance from the rotation. Right? We can think about how that changes. If you look at this rotation, you can think if something were really far away from that, it would have to move, the distance it moves to rotate 2 pi is going to be a much larger distance than if it's really close and rotates 2 pi. And so this r is going to kind of, this mass radius relationship is going to give us a way to kind of track how that mass is going to relate to that. This allows us to rewrite this thing, and we can get a Hamiltonian equal to negative h bar squared over 2I. Let's do this. D by d phi squared. Some psi. I'm going to leave it as psi for now, even though we know it's going to be written as a y later. I'm going to leave it as psi now, just because that's what we're used to. Plus v of x psi is equal to e psi. Again, in this situation where I'm just saying the radius is fixed, I'm not saying it's held because of any force or anything else, I'm going to say that this v of x term There's no potential being applied. This is somewhat unrealistic. There has to be something holding this thing together. But really, we can think about it in terms of like if you had a diatomic molecule, you can imagine that it's just spinning around like one atom is sitting still and the other atom is spinning around it. So this isn't completely unreasonable. There's no potential involved with that. It's just rotation. So that's completely feasible. So we can erase that. And I hope you can see the train coming. So we're going to multiply 2i negative h bar, bring the e over. We're going to get a really familiar looking equation that you're all going to be able to solve in your minds right now. Does that look familiar? I'm going to call that some constant squared. I don't want to use k again, right? We used k for particle in a box. We used kappa for particle in a well. I need to use something else, and I don't know. I'm just going to randomly pick m sub l. I don't know why I pick m sub l, but you know, m sub l and even some m sub l squared, you know, maybe that would make sense for some reason. No, we're picking this because we know what this is going to relate to in the future. We could call it anything, and the same physics, the same chemistry is still going to come out of that. We're jumping to the m sub l definition now because that's the convention that other people have already set up for us. We can then say, this is what we're trying to get to, this idea here, where theta is a constant. So it's going to be even more simple than this. What function? Yeah, question.
Should the term before ML be positive?
No, because when we multiply by the negative, and then, oh yeah, no, it should be positive. You were absolutely correct. Oh. Yes. Thank you. Very important. That, and I probably would have found that out as I went to this next step and then been like, why isn't it working? Again, pay attention to your negative signs. Track your negative signs. They're easy to drop, clearly. What should I write as my wave function that's a solution to this? What are some possibilities? Not thinking about the physical space, but just thinking about this differential equation. Take the derivative with respect to phi twice, get the same thing multiplied by some constant. E functions. Positives are positive, negative, imaginary, real. Say it loudly to your neighbor. Louder so I can hear you. Positive, real, or imaginary? None of you actually said it loud enough for me to hear, but things like this, right? This is really particle in a box again, except for now our box is just like, we've just made it so the ends of our box are like touching each other. So instead of being a box like this, it's a box like this. It's not like this, it's like this.
So are we looking for the probability of being on the ring or within the ring?
So it's definitely on the ring, right? We've restricted ourselves to say that r is a constant. So now we can say where in the ring is it? Now, typically, again, because people smarter than us figured this out a long time ago, the same way that we picked the sign functions when we were doing particle in a box, it turns out for this problem, it is easier to use the exponential functions. We know those are equivalent to each other through the Euler decomposition. But now we can start to say, okay, how do I solve for these things? And we're going to look at this in terms of boundary conditions and the possibilities that we get out of this. First off, I want to point out that this is essentially the positive m sub l and the negative m sub l corresponds to spinning in the clockwise direction or in the counterclockwise direction. So we're looking at a particle just like when we saw a free particle moving, the ikx or the negative ikx was a particle moving one direction or the other. Same things here. We've got a particle spinning in one direction or the other direction. Right? So we've got both directions of motion possible. The boundary condition that we're going to have is psi of phi is equal to psi of phi plus 2 pi. Right? That is to say, any angle, if I spin back around on it, I better get the same answer. Right? This covers two things. I need to be single valued and I need to be continuous. This is going to look at both of those. This is going to end up giving us a restriction on our possible m sub l values from negative infinity to negative 2, negative 1, 0, 1, 2, all the way up to positive infinity. Still, it's going to end up being a counting number. It's going to end up being a counting number that's going to make it so we always get this condition to be true. And we've essentially restricted what our wave function can be. And in doing so, we've restricted what our energies can be, how fast this thing can rotate, and which speeds, even which velocities it could even rotate at. What momentums, what angular momentums it could actually have are going to be restricted by applying this boundary condition. And this essentially gives us the thing that we want to know about the particle in a ring. We've got our potential wave function. We could solve for the A and the B depending on how much it's moving. With the restrictions to m sub l's, we've got some energy restriction as well. And I'm trying to think about how much more I want to do in the time that we have left. I don't think I want to do too much more. We will get to the point where we go through a little bit of the algebra, and I'll show you that this operator that we're using, this negative h bar squared over 2mr squared d by d phi squared, that is essentially going to be, I'll just tell you now, that is going to be the LZ operator over 2I. Oh, sorry. LZ squared over 2I. That's going to give us the LZ. That's going to be the Z component of the angular momentum. In order to make a little bit more sense of that, we have to get into cross products in three-dimensional space, which I don't want to do with these last 15 minutes. So, because that's how much time we have left, right? Okay. I'll write down one more thing just to make sure that we've got this. The energy associated, so we've got wave functions associated with this, and always we're looking for wave functions and energies. The energy for this would be m sub l squared, h bar squared, over 2I. Right, so we're going to have some energies associated with this. We're going to have some wave functions associated with this. That m sub l is going to be restricted by our boundary condition. This is looking a lot like the particle in a box in a harmonic oscillator already. with a twist. See what I did there? Twist. Sorry. But it is still like the process we went through, the kind of solutions we were using, all of that is actually quite familiar. All of that is stuff we've seen before and we've done before. The interpretation is a little bit different, right? This is now the energy. This is essentially the energy associated with this rotation and how fast it can rotate in this space is going to be restricted to actual quantized single values, single like discrete values that are possible. But these are going to be eigenfunctions of the operator. This is going to be the eigenvalues of the problem. We've got our wave functions, which give us which are eigenfunctions of the Hamiltonian operator. We know that these wave functions should be orthogonal to each other. We should be able to do all of those types of calculations. And we will. Questions? Okay, I'm going to stop this.